Today I'm going to do section 2.4. There is no section 2.3. I had written a section 2.3 to help the understanding of section 2.4, but it really kind of just made it more complex than it needed to be. There is no section 2.3. So the next thing we'll do is 2.4. Just real quickly, let me do a couple review problems. They're not in the text or anything, just to keep you focused on what's test-worthy from the earlier section. So in section 1, the kinds of problems that are test-worthy would be something like this. Trying to think if one's going to work. And something like this. In section 2.2, we either had multiply or divide problems. I'll do a multiply because it's a little bit easier. Takes up less room. So these are all three problems that you should be able to do by now. They're all potentially something that I feel comfortable putting any one of these on a test. So I'll do all three of them. They all require a bit of factoring. When I ask you to find the domain, you should hopefully know that you have to ignore the numerator. So I'm going to ignore that x squared plus 5x plus 6. I'm going to solve the denominator equal to 0 to get the numbers that are going to be important in my answer, but it won't be the entire answer. And then after that, after I solve that, I'm going to write my answer. And for the most part, I'll write my answer like this: the domain of the x squared plus 5x plus 6 over x squared plus 6x plus 8 is all real numbers except, and the algebra gives me the numbers for this sentence. So I'm almost done with this problem. I just have to do the algebra part, but I should really focus on, in the domain, you only work on with the denominator. You don't factor and cancel. If you factor and cancel, you'll delete one of the numbers that needs to be part of the answer. So the x squared plus 6x plus 8 is going to factor into two parentheses. There's no minus signs needed because the problem doesn't have any minuses. There's no bottoms up because there's not a number in front of the x's. And when I go to factor it, my x's are first, my pluses, my signs, my last have to multiply to 8 and add to 6, and that's going to be 2 and 4, 4 and 2. Once we get the problem factored, we split the factors up. The x plus 4, we set it equal to 0, and the x plus 2, we set it equal to 0. For the x plus 4, you minus 4 from both sides to solve for x, and you get x equal to minus 4. For the x plus 2, you minus 2 from both sides, and you get x equal to minus 2. And those are the numbers that belong in my answer after the word except. So the domain of x squared plus 5x plus 6 over x squared plus 6x plus 8 is all real numbers except -4 and -2. And again, if you don't want to write your domain in words and you did the interval answer, if you did this for an answer, if you said the domain is -infinity to -4, union -4 to -2, union -2 to infinity, that's beyond okay. So one of those two answers would be what you're going to need to have. And if you did anything with the numerator, then you'd likely get the wrong answer. The next two problems, the reduce and multiply, are really both just factoring and canceling. I made all the factoring as easy as I could. So to do this middle problem, to reduce, I need to take the numerator and factor it, the denominator and factor it, and then do any canceling that happens. So I made both the numerator and the denominator so they don't need bottoms up. So I know that my first are going to be a couple of x's in both my numerator and my denominator. I didn't put any minus signs in, so I know that my signs are going to be plus and plus. In the numerator, after the plus signs, my numbers have to multiply to 6 and add to 5. My choices are 6 and 1 or 2 and 3, and 2 and 3 add to 5, 6 and 1 add to 7. So positive 2 and positive 3 should be my lasts. The x squared plus 6x plus 8, my lasts have to multiply to 8 and add to 6. My only choices of numbers that multiply to 8 are positive 1, positive 8, positive 2, positive 4. I'm going to pick positive 2, positive 4. Now that I have both the numerator and the denominator factored, I can cancel. Not actually those. I could actually cancel the x plus 2's, and my answer should be x plus 3 over x plus 4. I checked almost all the answers when I did the video for section 2.2. Just to save time, I'm not going to check this. Or I did this in 2.1. I checked those and I checked these. So if you aren't clear on how to check your answer, go back and watch the videos from sections 2.1 and 2.2 and it'll show you. The third problem that I have written here, so again, it's just a factor and cancel. There's 4 factorings that need to be done. I usually do left to right, bottom, top to bottom. The first factoring I'm going to do is the x squared minus 9. That's a difference of squares, so I get 2 identical parentheses, one with a plus, one with a minus sign. I just take the square root of that 9. The next thing I'm going to factor is the x squared plus 4x plus 3. Again, that's a 2 parentheses factoring. I don't need bottoms up because there's not a number in front of the x squared. There's no minus sign, so my signs are going to be a couple of pluses. After the plus signs, I have to write 2 numbers that multiply to 3 and add to 4, and that'll be 3 and 1. Next factoring, I'm going to factor the x squared plus 3x plus 2. Same strategy here. My first are a couple of x's. My signs have to be a couple of pluses. After those plus signs, I need numbers that multiply to 2 and add to 3, and that'll be 1 and 2. And in the last denominator, a couple of x's up front, a couple of plus signs. After those plus signs, my numbers have to multiply to 6 and add to 5, and that's 2 and 3. Now I can cancel any denominator with any numerator in the same fraction or between fractions. So these x plus 3's that are lined right up on top of each other can cancel. This x plus 1 can cancel with that x plus 1. This x plus 2 can cancel with that x plus 2. What doesn't cancel, the x minus 3 and x plus 3 don't cancel each other because they're not identical. And when you have minuses or pluses in a factor, you can't cancel unless they're identical. So you can't cancel the x minus 3 with the x plus 3 at all. And you'll just leave those where they were at. The x minus 3 I'll leave in the numerator. The x plus 3 I'll leave in the denominator. And I won't need the parentheses anymore because I've gotten rid of the factoring. So that's kind of the gist of what's test worthy in the first two sections that we've done. I could have kicked in a divide problem on top of this multiply problem, but I figured 3 is enough for now. This is going to be what I suspect a longer lecture than you'll care to sit through, so I should just get started with it. So the beginning of section 2.4 are a bunch of friendly problems in that they don't have letters, and when a problem doesn't have a letter, my calculator will do them. And I'll just do that right now. So problem 2, it's almost kind of silly to do this with a calculator, but I can. I'm supposed to take the fraction 3 over 10 and add the fraction 2 over 10. And when I do those, my calculator tells me the answer is 1/2. Being able to get an answer on my calculator, it's nice, but it's not going to help me when the problems have letters, because the calculator just doesn't do algebra with letters. So I should know how to get that answer of 1/2 by hand. And it's not terribly hard. Hopefully you already know how to do that. So for this problem, the two fractions already have the same denominator. And when you have two fractions with the same denominator separated by a plus sign, you can rewrite the two fractions as 1 as long as you put the plus sign between the numerators or add the terms in the numerator. So 3 over 10 plus 2 over 10 equals 3 plus 2 over 10, which is 5 over 10. And that's not what my calculator wrote for an answer, because the fraction 5 over 10 is reducible, and 5 over 10 reduces to 1/2, because if you divide the 5 by 5, you get 1, 10 by 5, you get 2. So the answer to problem 2 in section 2.4, so this is emphasized just in case you can't read this small font, this is the starting of section 2.4. The answer to problem 2 is 1/2. Problem 4 is a little bit trickier. It's a subtraction. I've got a double negative, but it's not terribly tricky. The nice thing about problem 4 is I could definitely do it on my calculator because it doesn't have any letters, and my calculator does well for problems that don't have letters. A good thing about this problem is it needs both kinds of negatives. So I wrote the fraction 3/5. I'm going to use this minus for the subtraction sign, and then I'm going to do my fraction, and for the minus 4, because it's a negative number, I use the minus in the parentheses. So negative numbers get the negative in the parentheses. That negative 4 is a negative number as opposed to a subtraction sign, and that minus is a subtraction sign, which is the one in the bottom right hand corner. So I entered the problem the best I could. When I hit enter, my calculator tells me that this answer is 7/5, which is the same as 1 2/5, which is the same as 1.4. I prefer what my calculator gives me, the improper fraction, but it wouldn't be wrong if you wrote a mixed fraction, and it equivalently wouldn't be wrong if you wrote a decimal, but I prefer the improper fraction if I had my choice. So I'm going to do this by hand now. Just like I did the last problem, I'm doing maybe more than I need to do. I'm going to write the two numerators together with their signs intact, the minus sign between the two numerators and the minus sign in front of the 4. I only need to write 1/5 because when you're adding or subtracting fractions, the denominator doesn't change, the numerator does. It would have been nice if when I wrote this as one fraction, if I would have put a parentheses around that 4 to make the two negatives stick out. It's not a deal breaker if you don't have it, but usually if you have two negative signs in a row, you put a parentheses around the number that has the second negative sign. And now I have a double negative, which I'm going to change to a positive, and then I'm going to add the 3 and the 4. And I get 7/5, which is exactly what I hope to get. So problem 6, all of a sudden I can't do on my calculator, but it's supposed to be similar to the problems 2 and 4. If you notice problems 2 and 4, the denominators of each of the fractions were the same, So I didn't have to worry about common denominators. I was just able to take the two fractions and immediately write them as 1. And that's going to be the case in problem 6. Problem 6 is set up so that I could immediately take the two fractions and write them as one fraction by putting the numerators next to each other with the appropriate signs. The denominator, just like the denominator in problem 2 and problem 4, doesn't change. You just get one of them. So this is the beginnings of doing problem 6. This problem 6 is a bit more like problem 2 than it is problem 4, in that the answer that I get when I make the two fractions into 1 is reducible, like 2 reduced 5/10 reduced to 1/2, whereas 4 7/5 really wasn't reducible, but you could write it differently. Problem 6, it certainly doesn't look reducible, but it turns out to be reducible. So in my efforts to get the best final answer, I'm going to simplify that numerator by combining the minus 18 and positive 6. I could do that in my calculator. I can go minus 18 plus 6 if I can't do it in my head. And so in the numerator, I'm supposed to get a minus 12 along with the 4a. So I can rewrite this problem as 4a minus 12 over a minus 3. That's a better answer than what's written above it, but it's not the best answer. Once we get the two fractions simplified to one fraction and we have the numerator simplified, we need to see if we can factor and cancel. And if you can factor the numerator and that factoring leads to canceling, you need to do it. And that's the case here. The numerator of this fraction has a common factor of a 4. If I factor out the 4 from the numerator, I'm left with an a minus 3. And the beauty of that is that a minus 3 that's left after I factor out the 4 cancels with the a minus 3 in the denominator. Technically, the a minus 3 turns into a 1 in the numerator and the denominator. That's really when you're canceling, you're rewriting it as 1 over 1. And the numerator is just 4 when you do the multiplication or just cancel the a minus 3's. And I don't need to write a denominator, a fraction with a denominator, when its denominator is just 1, because any fraction over 1 is just equal to the numerator. So a best answer for problem 6 is just the number 4. Just like we did in the last couple sections, we can check. We can check by taking any number that's not, any number that doesn't make a denominator 0 and plug it in for the letter. So I like using 2, so I'm going to let a equal to 2. I'd like to plug that 2 into my original problem and my answer. There's no room for plugging a 2 into my answer. Since there's no letter in my answer, this tells me that when I plug a 2 in for a into the original problem, that it better reduce to 4. This says an answer of 4 says no matter what number I change a to, the whole fraction should reduce to 4. So if I don't get 4 here, I'm going to figure out what I did wrong. So I'm going to try to do this the best I can. So fraction 4 times 2 minus 18 over 2 minus 3 plus fraction 6 over 2 minus 3. So that apparently looks more or less like that. And when I hit enter, because it says 4, I feel good about my answer, because what I got when I plugged in 2 for a is the same as my answer. That makes me feel like I'm correct. It's not technically the perfect way to check, but it's the only way that really is practical. So I could pick another number if I wanted to. I could pick like 4 and plug it in for a and make sure I also get 4 when I do that, but that's getting to be ridiculous. Checking one number is usually more than sufficient. 8's a little bit trickier because of the minus sign. It's still, in my opinion, a friendly kind of problem in that the denominators are equal, and when the denominators are equal, you could immediately take the two fractions and write them as 1. What you can't do is be careless with your signs. When there's a minus sign between the two fractions, that minus sign will distribute through the right numerator. It'll attach to the first thing written in the right numerator. The first thing written in the right numerator was a z. This minus is going to attach to it. And it's also going to switch the sign in front of the 17. If I didn't switch this 17 from positive 17 to negative 17, and I went and I simplified and checked, it wouldn't check. So I'll show you. I'll pretend this is an error. If my first step would have said this, 5z plus 1 minus z plus 17, if you did that, and that's a super common error, your answer is not going to check. So this is not the correct way to solve. So I'll solve it the correct way, and I'll show you what happens if you solve it the wrong way. So for the correct way, I need to simplify the numerator, and in the numerator there's a 5z minus a z that need to be combined, and a plus 1 and a minus 17 that needs to be combined. 5z minus z is really the same as 5z minus 1z, which is going to be 4z. So as I go to simplify this problem, I made the two fractions into one. I was careful with my signs. 1 minus 17, I can do that without this calculator, but a lot of students like using their calculator, so I'll do it. 1 minus 17 is negative 16. So I get 4z minus 16 over z minus 4. Just like I did in the last problem, I'm going to factor the numerator. The numerator, there's a common factor of a 4. When I remove that common factor of a 4, I'm left with a z minus 4. The z minus 4s are going to cancel. I've canceled the entire denominator, so I don't need to write a fraction as my answer. The only thing I have left is the numerator of 4. Again, if I want to check, I like checking with 2, so I'll squeeze my checking in here. If I wanted to check, because my answer doesn't have a letter, I only need to pick a number and put it into the letter in the original problem. So I'm going to plug in 2 for z. I'll go 5 times 2 plus 1 over 2 minus 4 minus 2 plus 17 over 2 minus 4. If I get 4, then I think my answer is correct. So fraction 5 times 2 plus 1 over 2 minus 4 minus fraction 2 plus 17 over 2 minus 4. And when I do that, if I hit 4, I feel good. So I feel good about the top portion of the work. Let me go down to the bottom and show you how it doesn't work if you forget to change the sign on the 17. So I'm going to simplify. So I'm done doing the problem correctly. I'm doing the bottom version of the problem, which has a mistake. If I didn't change the sign on the 17, when I simplified the numerator, I'd still do my 5z minus 1z and get 4z. And then I do 1 plus 17, which is 18. I'd still have the z minus 4. The numerator would still cancel. Factor. I could factor out a 2 from the numerator. And if I factored out a 2, I'd be left with a 2z plus 9. In the denominator, I'd have a z minus 4. For this answer to be correct, this is a wrong answer, I'd have to get 4 when I plug 2 in for z, because when I plug 2 into the original problem for z, I get 4. I would have to get 4 when I plug 2 in for z into this answer. So if I wanted to check this wrong answer, I'd have to go 2 times 2 times 2 plus 9 over 2 minus 4. And for that to be right, I'd have to get 4, because that's what I got when I plugged 2 into the original problem. So I'll do that checking. I'm going to go 2 times 2 times 2 plus 9 over 2 minus 4. And when I do that, I get minus 13. So plugging 2 into the original problem, I get 4. Plugging 2 into this wrong answer, I get minus 13. I know this answer is not correct, or I messed up with my calculator, but I already know the mistake that I made. So it's super important to watch your signs when you're dealing with subtraction and the right numerator having a binomial in it. So this switching right here, if you don't do that and you keep the sign, the answer that you get is going to be wrong. 10, same structure. It's a subtraction problem. I have to watch my signs. It's still a friendly-ish problem because the right numerator, each fraction has the same denominator. So just like I did for problem 8, I'm going to write the two fractions as 1, and only when there's a minus between the fractions do you have to worry about the sign so much. The minus is going to attach to the x, and it's going to switch the sign in front of the 3. The sign in front of the 3 was minus, it switches to plus. Now I'm going to simplify by combining like terms in the numerator. In the numerator is a 2x minus x and a minus 5 plus 3. The 2x minus x is really 2x minus 1x, so it's going to be 1x. I don't have to write the 1, but I can write the 1. The minus 5 plus 3, I can do that, but I'll do it on my calculator. Minus 5 plus 3 is a minus 2. That fraction's numerator doesn't factor, and unlike the last few problems, it doesn't reduce, because you can't cancel a term with a minus unless there's something absolutely identical on the opposite side of the fraction. An x minus 2 will only cancel with another x minus 2. Let me go ahead and check. I'm going to plug in 2 for x in my answer and the original problem. So I'm going to go 2 times 2 minus 5 over 2 plus 1 minus 2 minus 3 over 2 plus 1. And I'm also going to do, that was really a bad choice of a number. Oh well. Then I'm going to do 2 minus 2 over 2 plus 1. The reason it's a bad choice of a number is I'm going to get 0 for each of these. And I don't like getting 0, I like getting a non-zero number, but I'm going to live with this for now. So I'm going to do 2 times 2 minus 5 over 2 plus 1 minus 2 minus 3 over 2 plus 1. I get 0. And when I do the other side and do fraction 2 minus 2 over 2 plus 1, I also get 0. I don't like getting the 0. Let me try another number. I'm going to try, how about 4 for x? Let me try to make sure it still works for 4. I'm going to go 2 times 4 minus 5 over 4 plus 1 minus 4 minus 3 over 4 plus 1 for putting 4 into the original problem, and then plugging 4 into my answer, I get 4 minus 2 over 4 plus 1. Just because I got a 0 and 0 is like too trivial of an answer, I'm going to check another number and make sure I get the same number again. And if I get the same thing twice that checks, then I'm feeling much better about my work. So that's putting 4 into the original problem for the x's. And when I do that, I get 2/5. When I plug 4 into the original problem, or my answer should I say, I go 4 minus 2 over 4 plus 1. I also get 2/5. So I double checked it. You don't really have to double check it, but the zeros made me a little bit worried. If you would have reduced this fraction at all, neither of the numbers would have likely checked. So if you went to the checking phase, plugging a number in for x into the original problem, it either wouldn't equal your answer or it wouldn't equal what you get when you plug the number in. So the nice thing about the checking, it'll check you make you not overdo it. So that is not a reducible fraction, even though you might think it's reducible. But the minus between the x and the 2, and x minus 2 can only cancel with another x minus 2. Similarly, an x plus 1 can only cancel with another x plus 1. 12 is still a friendly problem because the fractions have the same denominator. And when you're adding or subtracting, and when fractions have the same denominator, you just need to write the numerators next to each other. I don't have to be ultra careful with my signs like I did in the last couple problems, because there's only one term in the numerator. So that negative is going to attach to that 9, but there's nothing more fancy to do than that. So now I have the two fractions written as 1. I want to attempt to factor and cancel, and that numerator is factorable. It's a difference of squares. It's going to factor into x plus 3 times x minus 3. The x plus 3's are going to cancel. It made me cancel the entire denominator, which means I don't need to write a fraction for my answer. I just need to write what's left in the numerator. And what's left in the numerator is just an x minus 3. Again, I'll try checking with 2 again. So for checking, I'm going to plug 2 into the original problem. I'm going to go 2 squared over 2 plus 3 minus 9 over 2 plus 3. And then I'm also going to plug 2 into my answer. I'm going to go 2 minus 3. Hopefully I get the same numbers. If I get the same numbers, I believe my answer is correct. So first bit, 2 squared over 2 plus 3 minus fraction 9 over 2 plus 3. And when I do that, I get negative 1. For the other half, if I do the 2 minus 3, I get negative 1. Because my answers are the same, I feel good about my answer. 14, I don't have to change signs like I did previously. This plus sign is going to attach to the 3a, and I'm not going to have to change the sign with the minus 4. So I'm going to make the two fractions into 1 like I've been doing, but pluses are signed forgiving, and they don't change signs. So when I made the two fractions into 1, I put the two numerators as 1, didn't change any signs, and now I'm going to go into factoring and canceling. The numerator factors into, I need plus and minus for my signs, so it's either going to be a plus 1 minus 4, plus 4 minus 1, or plus 2 minus 2. And this is the pair I'm going to need, because 4 minus 1 gives me the 3. The 1 and negative 4 would give me a negative 3. The 2 and the minus 2 would give me 0. So I need a plus 4 and a minus 1. I'm going to cancel the a minus 1s, which makes my answer not need to be a fraction. I'm going to have just what's left in the numerator and a non-fraction answer. Again, I'm going to check with the 2's again. So I'm going to go 2 squared over 2 minus 1 plus 3 times 2 minus 4 over 2 minus 1, plugging 2 into the original problem for a. And I'll also plug 2 into my answer. So checking the original problem, 2 squared over 2 minus 1 plus fraction 3 times 2 minus 4 over 2 minus 1. I get 6. Means if I get 6 when I plug in 2 for x into my answer, I feel good about my work. And I'm not even going to use my calculator. That's silly. 2 plus 4 is just 6. So my answer, I've checked it the best I can. So I think we're done with the easy part of the section. Up through problem 14, every fraction had equal denominators. That's not the case for the next few problems. I should make a few problems up with just numbers. So before getting to the next problem. So this is just a review that's not from the handout. So if I gave you these fractions, 2/3 plus 4/5, and ask you to add them, because they don't have letters, my calculator can do them. So I could go 2/3 plus 4/5. When I do that, my calculator tells me the answer should be 22/15. Unfortunately, if I just added the 2 and the 4 and got 6 and added the 3 and the 5 and got 8, that's not going to be 22/15, and that's not the way we add fractions. When fractions have unlike denominators, you need to get common denominators. My calculator kind of clued me into I need to make the denominators 15. To make each fraction have a 15, I have to multiply its numerator and denominator by something to change the denominator to the 15. So the first fraction, I'm going to multiply by 5/5. Multiplying a fraction by the same number in the numerator and the denominator changes the appearance of the fraction, but not what the fraction reduces to. 10/15 reduces to 2/3, and 12/15 reduces to 4/5. So I can take the two fractions, rewrite their denominators to be the same, and then once I have each fraction written with the same denominator, then I can add the numerators together and get my answer. So this 22/15 you get by adding the 10 and the 12, which are the numerators when the fractions are made to have the same denominator. Let me do one more of these. So I'll do this on my calculator again, and then I'll do it by hand. So fraction 1/4 plus fraction 3/16. And the answer to this is supposed to be 7/16. Again, if I just added the 1 and the 3, I'd have a 4, so that's not good. My calculator helped me understand that the least common denominator was 16 if I didn't already know that. I need to make each fraction have a 16 in the denominator. For the first fraction, I'm going to multiply it by 4/4. The second fraction already has a 16 in the denominator. I don't need to multiply it by anything. I can leave it at 3/16. So I can rewrite the first fraction as 4/16, leave the second fraction 3/16, and then I could make the two fractions into 1 and make this 4 plus 3/16, and that will take me to 7/16. So when we're adding and or subtracting fractions that start off with different denominators, I'm going to need to multiply a numerator and a denominator, possibly of one fraction, possibly of both fractions, to make the denominators the same. Once I get the denominators to be the same, then I can add the fractions like I did in the first few problems. So this is an example where both fractions denominators needed to be changed. Here's an example where only one of the fractions denominators needed to be changed. But because the fractions started with different denominators, you can't just go straight into the adding. Each of the problems that we did in the first 15 or 14 problems, if you look at any of the problems that we've done so far, you looked at the left fraction and the right fraction, they had equal denominators, and that just made those problems infinitely easier. So now, digging into the mess that is this rest of this section, this is the hard part. So I need to make these denominators the same, and they're not the same. Which means I have to do a bit of work to either one of the fractions or both of the fractions before I can make the two fractions into one. And this has two letters, so the checking is going to be harder because I need to pick a number for each letter. So if I was doing this, for me, it's easy to see what I need to do, but I've taught this class so many times, it should be easy for me. This isn't really something you have to do, but if I write that second fraction without the exponent, you'll notice that the second fraction in its denominator has two y's and a z. My first fraction only has one y and a z. If I want to make these denominators look the same, I need to give this fraction another y. So if I just did this, if I gave this fraction another y by multiplying the numerator and the denominator by a y, both fractions would have two y's and a z, which would be good. Doing this multiplication of y over y, I can simplify this denominator by multiplying the y's. Two y's give me a y squared and leaving the z. And I can rewrite this denominator in its original form. So now I have the two fractions with the same denominator. I can add the numerators or combine the numerators together, write the 7y, which is the left numerator, followed by a plus sign, then the right numerator, which is the 6, over y squared times z. I'd like to factor and cancel, because this y squared and z can't cancel with a 7y plus 6. A 7y plus 6 can only cancel with another 7y plus 6. The only chance of being able to cancel something between the numerator and the denominator is if the numerator would factor, and the numerator doesn't have an exponent, so I'm not going to get a 2 parentheses factoring. It doesn't have a common factor, so I can't even get a 1 parentheses factoring. Because the numerator doesn't factor, I can't simplify this. I can't cancel the y's. If you cancel the y's, I'll show you what happens. Real quickly, I'm going to check, and then I'll show you what happens wrong if you check a wrong answer. So I'm going to let y equal to 2 and z equal to 3. In the original problem, I'm going to go 7 over 2 times 3 plus 6 over 2 squared times 3. I'm going to put that times sign in. And then I'll do the same for my answer. In my answer, I'm going to plug in 2 for y, and I'll go 7 times 2 plus 6 over 2 squared times 3. If my answer is correct, plugging in 2 for y and 3 for z in the original problem, plugging in 2 for y and 3 for z for my answer should give me the same numbers. So let me do this. Top one, 7 over 2 times 3 plus 6, delete, arrow, plus 6 over 2 squared. I don't think I need a times sign, but I'm going to put a times sign there just because I'm worried how that exponent's going to be thought of. And when I do this, I get 5/3, which means I better get a 5/3 when I do this bottom computation. So for the bottom computation, I go 7 parentheses 2 plus 6 over parentheses 2 squared times 3. And when I do that, I also get 5/3. So my answer is correct, and this would be completely wrong. If you did this, this is a common error. Not all fractions are reducible. And if in this problem, if you would have expanded the denominator and canceled out a y, and did that, and wrote this as 7 plus 6 over yz, or 13 over yz, if for that problem you plugged in, for that answer you plugged in 2 for y and 3 for z, you'd get 13 over 2 times 3. If I did that, if I did 13 over 2 times 3, I'd get 13 over 6. 13 over 6 is not 5/3, because when I did plugging 2 and 3 into the original problem and plugging 2 and 3 to this mistake answer, 7 plus 6 over yz, or 13 over yz, I can tell that that's not correct. So this is just not a reducible fraction. Most of the problems between 15 and 32, the numerator is not factorable and the fraction isn't simplifiable. 18, again, it has the multiple letters, which makes it not good. And there's a lot of work going on. Both fractions need to be improved upon. I need to make their denominators the same. The first thing I look at are the numbers. I see a 6 and I see a 9. Those aren't the same numbers. I want to make them the same numbers. And I know I can turn a 6 and a 9 into an 18. So to start, I'm going to multiply the left fraction by 3 over 3, the right fraction by 2 over 2. If that's all that I did, it wouldn't be enough. If I started there, this would give me 15 over 18xy minus 4y over 18x. Although that would be a good start, it's not enough because it doesn't make each denominator exactly the same. If I look at this version, both denominators have an 18x. This one has a y, that one doesn't have a y. I needed, for this second fraction, to give it the y in its denominator. So for the second fraction, multiplying by 2 over 2 wasn't enough because it didn't make the denominators the same. But if I did that, I'd go 2y times 2y. I'd multiply the 2 and the 2 and get 4. I'd multiply the y and the y and get y squared. And then 9x times 2y, I multiply the 9 and the 2 and get 18. I leave the x and the y next to each other. So what I need to do to make the two fractions combinable to one fraction by subtraction, the first fraction needed to be multiplied by 3 over 3. That gave me the 18 that I wanted to turn the numbers into. Second fraction multiplied by 2y times 2y. Multiplying by 2 turned the 9 into an 18. Multiplying by y gave me that extra y. Now I'm going to combine the two fractions into one. And I'm going to be done, and I'm going to have an answer. It always is possible when you make two fractions into one that the numerator can be simplified. In this case, you can't subtract the 15 and minus 4 and get an 11 because the 15 isn't a like term. It doesn't have a y squared. And that doesn't factor. This 15 would have to be like a 25 or a 49 or a 36 for this to be a difference of squares. So this is non-factorable, non-reducible. This is just the answer. I'm going to stick with that 2 and 3. I'm going to plug in, for my checking, I'm going to plug in 2 for x and 3 for y. So I'm going to go 5 over 6 times 2 times 3 minus 2 times 3 for y, 6 for 2 for x. So I'm going to plug in 2 for x, 3 for y into the original problem, and 3 for y, 2 for x into my answer, and hopefully those come out to be the same. So I'll do this first, that second. If I get the same numbers, I feel good. So fraction 5 over 6 times 2 times 3 minus fraction 2 times 3 over 9 times 2. And so when I plug in 2 for x and 3 for y in the original problem, I get negative 7 over 36. Do the same for my answer. For my answer, I'm going to go 15 minus 4 times 3 squared over 18 times 2 times 3. And I also get negative 7 over 36. So because I have the same numbers, I feel good about my answers. Again, if you did try to do any reduction on this, if you would have canceled the y's or canceled the 15 with the 8, if you tried to do the checking, you wouldn't get that match, and you'd find that you had a mistake. So if you're working ahead of me, problem 20 can be done a couple of different ways. A lot of students will look at problem 20 and realize just multiplying this fraction, that x plus 4 by 5 will give you a 5x plus 20. If that's all you did is multiplied the first fraction by 5 over 5, you did perfect. If you didn't do any factoring, it's okay. I'm going to do this problem the way it's going to be beneficial for more complex problems. So I'm going to take the right denominator and factor it. So generally in the adding or subtracting problems, if a denominator is factorable, you factor that denominator. And this denominator of 5x plus 20, there's a common factor of 5 that I could factor out. Now I look at the two fractions. The denominators both have an x plus 4. I'm going to put this x plus 4 in a parentheses. It's not necessary to have that parentheses, but it's not wrong to have it there. And now it should make it more clear on what I have to do to make the two fractions have the same denominator. Regardless of if you factor or if you don't factor, you have to multiply the left fraction by 5 over 5 to make the two fractions have the same denominator. If I multiply the left fraction by 5 over 5, I'd multiply the 5 and the 2x and get a 10x. And then it's kind of up to you, but normally we don't multiply out factor denominators. If you had a 5x plus 20 in the denominator, it's completely fine. But it might make you miss a canceling if this thing would happen to cancel. Factor denominators make it easier to see canceling than non-factored. So now I have the two fractions with the same denominator. I'm going to combine the two fractions into one by writing their numerators next to each other. The minus between the two fractions will make me switch this sign. The minus is going to attach to the x and switch the minus to a 4. And now I'm going to simplify the numerator. In the numerator, the thing that's going to simplify is the 10x minus x, and that's really 10x minus 1x, which I'm going to write as 9x. Simplifying the numerator doesn't do anything to the denominator. Whether I have 5x plus 20 or what I have, when I subtracted the 10x minus x, I didn't need to change anything. Now I look at this, it almost looks like it's reducible. It looks like I could cancel the x plus 4s, but I can't. If this 9 was in a parentheses next to an x plus 4, I could cancel. If I had something like this, 9 times x plus 4 over 5 times x plus 4, that's cancelable because the x and the 9 are separated. This is not reducible. There's no common factor, so I can't get a 1 parentheses factoring. There's no exponent, so I can't get a 2 parentheses factoring. And a 9x plus 4 can only cancel with a 9x plus 4. It doesn't cancel with a 5x plus 20, which is what this denominator would equal without the parentheses. But if you had 5x plus 20 in your denominator, that's okay too. So I have an answer. I'm going to check it by plugging in 2 for the x's. So I'm going to go 2 times 2 over 2 plus 4 minus 2 minus 4 over 5 times 2 plus 20. And down here I'm going to go 9 times 2 plus 4 over 5 times 2 plus 4, or 5 times 2 plus 20, depending if you have that factored or not. So in the numerator, I start off fraction 2 times 2 over 2 plus 4 minus fraction 2 minus 4 over 5 times 2 plus 20, and I get 11 over 15. Now I'm going to go to my answer and try the same. Fraction 9 times 2 plus 4 over 5 times parentheses 2 plus 4, and I get 11 over 15 again. And that's a beautiful thing. So because when I plugged in 2 for x in my answer, as well as in the original problem, because I got the same number, I feel good about my answer. And again, if you attempted to reduce this and did any sort of canceling, you should notice that your answer is wrong, because if you cancel the x's out, then it would have to be 11 over 15 for an answer. And if you didn't cancel the x's out and you plugged 2 in for x, you wouldn't get 11 over 15. On 22, it's a tough problem. Both denominators are factorable, and I'm going to factor them first. The left denominator, there's a common factor of a 3. And I'm going to factor out that common factor of a 3. And when I do that, I'm left with a y minus 7. The right denominator, there's a common factor of a 4. When I factor that out, I'm going to be left with a y minus 7. So both denominators have a y minus 7. What they don't have in common is they have different numbers in front of the parentheses. I want to make the numbers in front of the parentheses the same, and I'm going to make them into a 12 because the least common multiple between 3 and 4 is 12. So I'm going to multiply the first fraction by 4 over 4. I can multiply to the left or the right of the fraction, it kind of doesn't matter. And the second fraction I'm going to multiply by 3 over 3. That will make me have 12s in each of the denominators along with the y minus 7s. When I simplify the numerator, that 4, I have to kind of pretend like there's a parentheses here and multiply it by both the 6y and the 1. And the 3 I have to multiply by the 2y and the 1. So I'm going to multiply out the numerators, but usually we don't the denominators. When we're adding or subtracting fractions, it's common to leave the denominators factored, but to multiply out the numerators. So both of my denominators, although I could write them as 12y minus 84, I'm just going to leave them as 12 times y minus 7. The left numerator I'm going to write as 24y plus 4 by multiplying 4 by 6 and 4 by 1. The right numerator I'm going to write as 6y minus 3 by multiplying this 2 by 3 and that 1 by 3. Now the two fractions have the same denominator, and when we have that set up, I can make the two fractions into 1 by writing their numerators next to each other. I don't have to worry about changing any signs because there isn't a minus sign between the fractions. So now I have the two fractions written as one fraction. I'm going to simplify the numerator, and to simplify the numerator, I'm just going to combine like terms. And that's not terribly hard to do. I'm going to add the 24y and the 6y to get a 30y. I'm going to add combine the positive 4 and minus 3 to a 1. So in my numerator, I'm going to get a 30y plus 1. In my denominator, I'm going to get a 12 times y minus 7. The numerator doesn't factor. There's no common factor, so I'm not going to get a 1 parentheses factoring. There's no square. I'm not going to get a 2 parentheses factoring. A 30y plus 1 can only cancel with another 30y plus 1, so this isn't going to cancel, and this is just going to be my answer. Most of the bottom problems that have unlike denominators don't factor and cancel, like the beginning. Let me check with 2's again. I'm going to plug 2 into my original problem. I'm going to go 6 times 2 plus 1 over 3 times 2 minus 21 plus 2 times 2 minus 1 over 4 times 2 minus 28 and get a number. And I'll do the same for my answer. I'm going to go 30 times 2 plus 1 over 12 times 2 minus 7. If you'd written the denominator 12y minus 84, it's okay. It's preferred to leave the denominator factored, but it's okay if you unfactored it. I wouldn't take points off for it. So checking the numerator, checking the original problem, 6 times 2 plus 1 over 3 times 2 minus 21 plus fraction 2 times 2 minus 1 over 4 times 2 minus 28. So the original problem, when I plug in 2 for x, I get negative 61 over 60. Now I'm going to do the same thing for my answer. I'm going to go 30 times 2 plus 1 over 12 times 2 minus 7. And I get negative 61 over 60. Again, that matching number makes me feel good about my answer. The checking that I'm doing in this purpley color is completely optional, but it doesn't take but 20 seconds to check. And if these numbers didn't match up, then you know you've had a mistake. You've either over-reduced or you messed up somewhere, so you have a something to go looking for. 24 is tough-ish. Anytime when I'm adding or subtracting fractions that have unlike denominators, if any denominator factors, I should factor it first, and that's the case here. the right denominator factors, and it's a difference of squares. It's going to factor into two essentially identical parentheses, one with a plus, one with a minus sign. You get an m plus and an m minus 4. After I factor the right denominator, I notice both denominators have an m minus 4. The right denominator doesn't have an m plus 4. I'm going to put the m minus 4 in a parentheses. It just looks nice when I do this next step. I'm going to give the left fraction the m plus 4 that it's missing. Now my denominators are the same. When we're dealing with adding or subtracting fractions, we generally leave denominators factored. We generally multiply out numerators. So I'm going to multiply out that left numerator, but not the left denominator. So for the left numerator, I'm going to multiply 2 times m and 2 times 4 and get 2m plus 8. I should be writing equal signs because everything is equal to the line above it, but I get lazy and I don't do it. If you don't, it's not such a big deal. So the right fraction, I didn't need to do anything to it. It already had the denominator I was searching for. The left fraction, I did the work to make its denominator proper. Now I'm going to make the two fractions into one. And again, the minus makes me switch a sign, so I'm going to be careful here. I'm going to write 2m plus 8 for the first numerator. I'm going to attach the minus sign to the m, change the sign in front of the 2, and I'm going to leave the denominators as they were. And now I'm going to combine like terms in the numerator. In the numerator, there's a 2m minus m, which I'm going to consider 2m minus 1m, and there's a plus 8 and a plus 2. 2m minus 1m is going to give me 1m. I don't need to write the 1, but I can. Plus 8 and plus 2 give me a plus 10. The denominator, we wouldn't generally FOIL it out. If you wrote m squared minus 16, it's okay. It's just really not often done. The numerator doesn't have a square, so it's not going to give a 2 parentheses factoring, and it doesn't have a common factor either. M plus 10 can only cancel with another m plus 10, so this isn't going to cancel. And I think this is my answer. And again, I'm going to check. I like using 2, so I'm going to plug, well, 2 is going to give me a 0 here. Let me use 3, but 2 would be fine, but I'm going to do 3 this time. I'm going to go 2 over 3 for m minus 4 minus 3 minus 2 over 3 squared minus 16. And for my answer, I'm going to go 3 plus 10 over 3 minus 4 times 3 plus 4, just to see that I get the duplication that I want to get. So checking the original problem, 2 over 3 minus 4 minus fraction 3 minus 2 over 3 squared minus 16. So plugging in 3 for m as opposed to 2, I get negative 13 over 7. It would be okay if you plugged in 2. If you plugged in 2, you'd get negative 1, and that would be fine. But I liked plugging in 3 just because 2 made that numerator 0, and that was almost too trivial of a number to pick. Now I'm going to check my answer. I'm going to go 3 plus 10 over 3 minus 4 times 3 plus 4. I hope like heck I get negative 13 over 7. Beautiful. So again, it takes me 30 seconds to check, and that will possibly save you on a test from doing something that you shouldn't do. So if you got to a fraction answer and you reduced it, that's a lot of times where students make mistakes is they get the right answer, then they reduce it too far. The checking will show you if you've reduced it too far. So most of the problems when the denominators aren't the same, they just can't be reduced. Whereas the beginning problems that started with like denominators, most of those could be reduced. So just like the last few problems, I see a denominator that's factorable. The denominator on the left has a common factor of an x because each term to the left and right of the plus sign has an x. So I'm going to factor out an x. From the 3x squared, it started with 2 x's. I took 1 away. I'm left with the 3 and 1 of the x's. The 5x, I took its x away, I'm only left with a 5. The second fraction doesn't have a common factor, so I can't do a 1 parentheses factoring. It doesn't have an exponent. I can't do a 2 parentheses factoring. So the right denominator doesn't factor. I look at my two denominators. I'm going to put this 3x plus 5 in a parentheses again just so they start to look more alike. And I realize that if I multiply the left denominator by x over x, I'm going to have exactly the same two denominators. So I can leave the first fraction in its form that it is already. And in the second fraction, I'm going to multiply that x times 2. And x times 2 is just equal to 2x. I'm writing a plus sign here. And again, we normally, when we're adding or subtracting fractions, don't multiply out denominators. So I'm going to leave my denominator intact. Now I have the two fractions written with the same denominator. I'm going to combine them into one. In the numerator, I'm going to combine like terms, which is the x and the 2x, which really is a 1x and a 2x. So in the numerator, when I combine those terms, I'm going to get a 3x. That numerator has a common factor. I should probably factor it out. So I'm going to factor out a 3 from the numerator. And when I factor out a 3 from the numerator, I'm left with an x plus 1. Still doesn't cause any canceling to be possible. An x plus 1 can only cancel with another x plus 1. So no canceling can be done. I would consider this factored numerator with the best answer. This unfactored numerator would be an okay answer. It's kind of, if the factoring doesn't lead to canceling and you miss the factoring of the numerator, it's not horrible. Check again. I'm going to plug in 2 for x. So I'm going to go 2 plus 3 over 3 times 2 squared plus 5 times 2 plus 2 over 3 times 2 plus 5. I'm going to go to my answer and go 3 times 2 plus 1 over 2 times 3 times 2 plus 5. Do those real quickly to make sure my answer and my original problem match up when I plug in 2 for x. So 2 plus 3 over 3 times 2 squared plus 5 times 2 plus fraction 2 over 3 times 2 plus 5. And in my original problem, when I plug in 2 for x, I get 9 over 22. I'll go to my answer and do the same. Fraction 3 parentheses 2 plus 1 over 2 parentheses 3 times 2 plus 5, close up my parentheses, and I get 9 over 22 again. So I don't think I made a mistake. If I would have plugged in 2 for the x's in this okay answer, I also would have gotten 9 over 22. I knew this was going to be a long section. I'm wearing out. Which is kind of unfortunate, but it is what it is. 28's a tough problem. 28 will not be on the test, so it's not test worthy. It has a trick where you need to factor out a -1 to make the denominators the same, and that's a trick that I don't do a lot of in the homework. And because I don't do that many of them on the homework, and because it's not that important of a skill, you're not going to see it when you get to the test or the review. So neither denominator is factorable. There's no exponent, so I'm not going to get 2 parentheses. There's no common factor either. But the denominators aren't the same. So I'm going to get the denominators to look the same by taking the first fraction and writing its denominator with the y first and the 2 second. That numerator 6 minus 2y is factorable. Normally I hold off on factoring the numerators to the last step. Now that I have the denominators written kind of better with the y's first and the number second, from the first denominator I'm going to factor out a -1. And when I factor out a -1, I'm going to flip the sign on the y from negative to positive. I'm going to flip the sign on the 2 from positive to negative, because when you factor out a negative, you change signs. The denominators still aren't the same, but I can certainly do this division right now. I can divide 3y by -1, because the 3y doesn't have an adding or subtracting between the 3 and the y. I can cancel or divide it with a -1. So I'm just going to divide this 3 and this -1 and get the -3 up to the numerator. When I do that division, the negative leaves the denominator and winds up in the numerator. Now I have the two fractions written with the same denominator. I can make the two fractions into one. The minus is going to attach to the 6, and it's going to switch the sign on the 2y to positive. So now I'm going to simplify the numerator by combining the -3y and positive 2y. That's going to give me a -1y. So when I combine the numerators, I get -1y minus 6 over y minus 2. This would be an okay answer, in that the numerator is correct. It's just written odd. A better answer, or the best answer, would be to factor out a -1 from that numerator, because both terms have a negative. If I factored out a -1 from the numerator, the negative y would turn to a positive y, the -6 would turn to a positive 6, and then I'd have a y minus 2 down low. Because I know this isn't on the test, and I don't want to do a lot of time with it, I'm just going to skip the checking. If I was checking this, I wouldn't plug 2 in for y, because that would make a denominator 0. I wouldn't probably plug 3 in for y, because that would make that numerator 0. I'd probably put 4 in for y, but I'm not even going to do that, because like I said, there isn't going to be a problem where you're going to have to factor out a -1 and make the two fractions subtract or add fractions. Getting close, but I still think there's a chunk of problems to go. Oh yeah, there's still still 7 problems to do. So I'll just keep plodding along. But if you're burnt out, it wouldn't be the worst time just to pause the video and come back at another time, because I'm fading out and I know how to do this stuff. So this has got to be brutal to be watching this. So for 30. I'm going to factor the first denominator, and I'm going to factor the second denominator, because they're both factorable. And they're both easy-ish factoring. The first denominator, I have to make 2 parentheses. I don't get minus signs, because the problem doesn't have any minus signs in the first denominator. And the numbers after the plus signs need to multiply to 4 and add to 5. And 1 and 4 would do that perfectly. The second fraction is just a difference of squares. It's going to factor into b plus 4 and b minus 4. I want the denominators to have all the same pieces. They both have a b plus 4 in common, which is good, but each fraction has something in its denominator that the other one doesn't. The second fraction has a b minus 4 in its denominator. I need to make the first fraction also have that b minus 4. The first fraction has a b plus 1 in its denominator that the second fraction doesn't have, and I need to make it have that. So doing this, factoring the denominators, multiplying the first fraction by b minus 4, multiplying the second fraction by b plus 1, makes the denominators have the same 3 pieces, but they're not in the same order. That's not a big deal, because when you're factoring, the order that you write the parentheses in isn't important. I'm going to pick an order and write the things in the same order. So my next step, I'm going to multiply out the numerators. I'm going to multiply a 2 times b in the left numerator, and a 2 times a minus 4. and the left fraction is going to have a 2b minus 8 in its numerator. And then I'm going to just leave the order. I'm content with this order: b plus 4, b plus 1, b minus 4. Second fraction, I'm going to multiply in the numerator 6 times b and 6 times 1. When I multiply 6 times b, I get 6b. When I multiply 6 times 1, I get 6. I'm going to write this denominator in the same order. I can shuffle these parentheses around. There isn't a right and a wrong order, but you usually write the same order. So I decided that that was the order that I wanted, but if you had the same three pieces in your denominator and the order was different, that's completely fine. So now the fractions have the same denominator. I can write the two fractions as one by combining their numerators. And when I combine two fractions with the same denominator into one, I don't change the denominator. I'm going to simplify the numerators now. I have a 2b plus a 6b and a minus 8 plus 6. The 2b plus 6b is 8b. The minus 8 plus 6 is minus 2. The numerator does factor. The factoring doesn't lead to canceling, so if you miss the factoring, it's okay. So this would be an okay answer. But if you factored out a 2 from the numerator and did 2 times 4b minus 1 over the three pieces, written in whatever order you decided to write them in, that would be the best answer. Complicated enough that I should check, and 2's fine because 2 isn't going to make any zeros. So I'm going to go 2 over 2 squared plus 5 times 2 plus 4 plus 6 over 2 squared minus 16. And I'm going to jam a 2 in here. I'm going to go, just can't fit this anywhere. 2 times 4 times 2 minus 1 over 2 plus 4 times 2 plus 1 times 2 minus 4. So plug 2 in for the b's in the original problem. Fraction 2 over 2 squared plus 5 times 2 plus 4 plus fraction 6 over 2 squared minus 16. I get negative 7 over 18 when I plug 2 into the original problem. And this mess that's barely readable, I'm going to try to do it next. I'm going to go 2 times parentheses 4 times 2 minus 1 over 2 plus 4 times 2 plus 1 times 2 minus 4. It best say negative 7 over 18, and it does. So I feel good about my work as I did the best check that I could do. Alright, so 32, 34, 36, 38, 40, 42, 44. 7 more problems, 3 minutes of problems gives me 21 minutes, hopefully, that I can do this so that I put you out of your misery. Oh, and then we're getting to problems that are even more messy pretty soon here, and those likely won't be on the test, so I'll talk about those when they come up. So each denominator is factorable. So I'm going to factor the denominators. The first denominator, I have no minus sign, so I don't have to worry about minus signs. There's no bottoms up because there's no number in front of the a squared. My last have to multiply to 1 and add to 2. It's just going to be 1 and 1. So the left denominator factors into a plus 1 and a minus 1. The second denominator, I know that my signs are going to be plus and minus. And my last, multiply to 4 and subtract to 3, and that's 1 minus 4. because 1 times negative 4 is negative 4, 1 minus 4 is negative 3. Both denominators have an a plus 1, which is good. This denominator has an a minus 4, this doesn't, so I'm going to give it an a minus 4 that it doesn't have. This denominator has an a plus 1, but it's not enough for it to have one a plus 1. It needs to have two a plus 1, so I'm going to give it that second a plus 1. Now I'm going to multiply out the numerators and write the denominators in the same order. So I'm going to go 6 times a, 6 times minus 4. 6 times a is 6a. 6 times minus 4 is minus 24. And I'm going to write this as a plus 1 squared. And this is a minus 4. The second fraction, I'm not worried about the minus sign yet. I'm going to multiply the 1 through the numerator, and 1 times anything is going to be itself, so I'm going to leave that a plus 1. And again, I'm going to write the denominator as a plus 1 squared times a minus 4, because I can multiply those a plus 1s and write them as a plus 1 squared. Now I'm going to worry about the minus sign when I make the two fractions into one. I'm going to take the left numerator and the right numerator, write them next to each other. I change the sign of the minus 1 because of the subtraction, and I leave the denominators how I have them written. You don't need to have it written exactly like mine, as long as you have something that's equal to mine. Now I'm going to combine the numerator. I'm going to do a 6a minus a and a minus 24 minus 1. 6a minus a is the same as 6a minus 1a, which is 5a. Minus 24 minus 1 gives me a minus 25. You could do that on your calculator if you can't do it by hand. Again, this leads me to what I would say is an okay answer, but not the best answer because the numerator factors, and I should factor out the 5 from the numerator. The thing is, factoring out that 5 from the numerator doesn't cause any canceling to happen. So it's not that big of a deal if I miss it. Alright, I'm going to plug in 2 for my checking. So I'm going to go 6 over 2 squared plus 2 times 2 plus 1 minus 1 over 2 squared minus 3 times 2 minus 4. And then down here I'm going to go 5 times 2 minus 5 over 2 plus 1 squared times 2 minus 4. And I'll do my best to show that those are equal to each other. So original problem, fraction 6 over 2 squared plus 2 times 2 plus 1 minus fraction 1 over 2 squared minus 3 times 2 minus 4. And I get 5 over 6, assuming I entered that right. I'm fading on myself and I'm not sure I actually entered that right. But I'm going to check down here and hopefully get 5 over 6 again. So I'm going to go 5 parentheses 2 minus 5 over 2 plus 1 squared. I'm going to put a times sign here. I may not need it. And then 2 minus 4. And I get 5 over 6 again. How lucky. Okay, so if this is as far as you went, I think this is really as far as you need to be. But I'm going to do the rest of the problems. The rest of the problems have lots of little evenness in them. There's some bottoms up factoring. 36 would be a good problem to do. 38 has bottoms up factoring. 40 has bottoms up factoring. And 42 and 44 are kind of funky. I just watched the video. It can't hurt to watch it, but I think the bulk of the test questions are likely to come from problems 1 through 32, and not so much from these. And I'm not supposed to do 33. I'm supposed to do 34 because 33 is an odd problem, and I saved that for you. So I won't do 33. never on a test would I make you factor with two letters. So I'm not going to expect you to be able to factor something like 33 nor 34. But 34, it's good to see, because every now and then you're asked to factor with both an x and a y. I'm going to go ahead and do that. The right denominator doesn't have a common factor, so I'm not going to get a 1 parentheses factoring. It doesn't have a square, I'm not going to get a 2 parentheses factoring, so it just doesn't factor. The left denominator, because there's nothing but plus signs, I'm going to get plus signs in my answer. I know I need to have x's up front to give my x squareds for my firsts, and my lasts need to have a couple of y's to get y squared for my lasts. If I foiled that out, my letters for my firsts would be x squared, my lasts would be y squared, which is good, but I wouldn't have the right number. The numbers that go in front of the y have to multiply to 2 and add to 3, and 2 and 1 will do that perfectly, and I'll even throw a 1 there. So this is how the left denominator factors. Again, I did that kind of fast, and I know I won't ask that on a test. Now I look at the denominators. They both have an x plus 2y. This one I need to tack on an x plus 1y. I don't have to write the 1, but I could. Since I already had it written, I'm writing it again. And I'm going to give that to both the numerator and the denominator. I'm going to multiply out that right numerator before I deal with the subtraction between the two fractions. I don't need the 1 in front of the y, but it's okay. In this numerator, if I ignore the negative, I'm going to multiply 4 times x and 4 times 1y and get 4x plus 4y. So now the two fractions have the same denominator. I'm going to combine the numerators together. Again, I'm going to be careful, and I'm going to switch that sign. So I'm going to go 3x, attach the minus to the 4x, switch the sign of the plus y to minus, and then I'm going to have x plus 2y over x plus 1y. In the numerator, I'm going to combine a 3x minus 4x, and that'll give me a negative 1x. So I get negative 1x minus 4y times x plus 2y times x plus 1y. This would be an okay answer, but not the best answer. Because the numerator, both terms are negative, it's probably nice to factor out a negative 1. If you factor out a negative 1 from the numerator, you're left with an x plus 4y. Doesn't cause any canceling because an x plus 4y doesn't cancel with an x plus 2y. But it's still, if a numerator is factorable, we generally do that factoring. Because I'm 100% certain I won't put a problem that has factor with two letters on a test, I'm going to skip the checking, because if you're still with me, you've got to be fading, because I'm a little bit woozy right now from doing this, and I know how to do it. So it's got to be way more intense to be just sitting through this. 36 bites because of the bottoms-up factoring. Left denominator is bad. Right denominator isn't bad. Right denominator doesn't have a common factor. It doesn't have an exponent. There's no factoring. Usually when we have bottoms-up factoring, I do it off to the side. So I'm going to attempt to factor that denominator of 2z squared. I'm going to emphasize minus 1z minus 3 using bottoms-up factoring. So I'm going to multiply first, and specifically I'm going to multiply this positive 2 and that minus 3 and get a minus 3. So I'm going to get z squared minus 1z minus 6. And then I'm going to factor. This is going to factor into z plus 2 times z minus 3. Really? That's horrible. Hold on. I realize 6, 2, 3. That's just flat out awful. I'm going to rewrite problem 36 so that when you print out the handout it doesn't say this. Let me finish up this factoring, and then I'm going to rewrite 36. That makes that insane in terms of the amount of work that would need to be done. So getting back to this factoring, I'm going to make this problem so it's not ridiculous here in a second. So I started off, I decided I wanted to factor this. Because of the 2 in front of the z squared, I knew I needed bottoms up. So I multiplied, factored. Now I'm going to divide, reduce, and bottoms up. I started off multiplying. Oh, I guess it's okay. I don't have to. I take that back. I don't need to change it. I was doing work in my head that I did wrong. So the divide, reduce, and bottoms up makes the first parentheses z plus 1. I divide. The second parentheses, I get 2z minus 3. Yeah, like I said, I'm getting a little loopy right now. This is actually okay. I don't need to change this. I thought something bad was going to happen in that the denominators didn't have any like pieces, and that would be evil. So now I have the left fractions denominator factored. The right denominator had nothing needed to be done to it. I need to make the denominators the same. And to make the left denominator the same as the right denominator, I need to multiply 2z minus 3 by the second fraction. Now the denominators are the same, which is a good thing. The first fraction, its numerator is just nice and friendly. Nothing needs to be done to it. So I'm going to leave the first fraction just like it looks right now. But the second fraction, I'm going to FOIL out its numerator. I'm going to leave the denominator alone. Usually we don't FOIL out factored denominators. But before we make two fractions into one, we usually do numerators. So this numerator, I'm going to go firsts of z times 2z, which is going to give me a 2z squared. And then I'm going to do outers. So I did first and then outers, which are z times minus 3z. Minus 3, should I say, which is going to give me a minus 3z. Then I'm going to do inners, which are going to be a minus 3 times 2z, which are going to be a minus 6z. And then I'm going to do lasts, which are minus 3 times minus 3, which is positive 9. So I have the two fractions written with the same denominator. Good. Now I'm going to take the numerators and write them as one big long numerator. So I'm going to get 2z plus 2z squared. I'm going to combine these to a minus 9z. I'm going to combine the outers and the inners to save myself a little bit of work. And when I make the two fractions into one, I don't need to change the denominators. I do need to simplify up the numerator. And in the numerator, there's a 2z minus 9z that I'm going to write as a minus 7z. So I'm going to get something that's probably the best answer, but that's possibly factorable. So I'm going to go 2z squared, and then 2z minus 9z is minus 7z, and then plus 9 over z plus 1 times 2z minus 3. I should attempt to factor this. So again, anytime I get a numerator that's potentially factorable, I should try to factor this, but I don't think it does. So I'm going to attempt to factor this 2z squared minus 7z plus 9. I'll do bottoms up factoring. I'll start off by multiplying. I'll get z squared minus 7z plus 18. And now I'm going to factor, or try to factor. I know that my signs have to be minus and minus, so that my lasts can only be minus 1 and minus 18, minus 2 and minus 9, or minus 3 and minus 6. I have to multiply to that 18, but add to this minus 7. 18 and 1 is 19, 2 and 9 is 11, 3 and 6 is 9. because I can't find a pair of numbers that multiply to 18 that add to 7, that means this is prime, and it doesn't factor. So in my attempt to factor, I knew I needed bottoms up because of the 2 in front of the z squared. Did my first step of my bottoms up, that's easy to do. The second step, I couldn't find lasts that multiplied to 18 that added to 7. These, because they have the same sign, they don't give me a -7, so they're not going to be good. So that doesn't factor, so this should be my answer. And I'm just boring out. Let me check this anyways. I'm going to plug in 2 for my answer and my original problem. I'll just sneak it on new fresh paper. So I'm going to check 2. I'm going to go 2 times 2 over 2 times 2 squared minus 2 minus 3 plus 2 minus 3 over 2 plus 1, plugging in 2 to the original problem. And then I'll go to my answer. I'm going to go 2 to, this x should be a z. It should be 2 times 2 squared minus 7 times 2 plus 9 over 2 plus 1 times 2 minus 3. Really wearing out. So fraction over here, 2 times 2 over 2 times 2 squared minus 2 minus 3 plus fraction 2 minus 3 over 2 plus 1, and I get 1. Wow. And this next down here, I do this, fraction 2 times 2 squared minus 7 times 2 plus 9 over 2 plus 1 times 2 minus 3. And I get 1, thank gosh. So I'm pretty good on this answer. I would guess this is more complex than I'd ask on a test. There might be a problem at this sort of level of difficulty on the review, just because I know in college algebra, Math 151, that these come up again at this level of difficulty. But I would be astonished if I did that to you on a test. So I'm going to keep trudging along and doing all the even ones just so you can have them in your notes, just in case you want them. First thing I need to do is factor both denominators. That's both side work. So I'm going to do bottoms up factoring for both. So I'm going to factor the 8m squared plus 15m minus 2. I start off, I multiply. I'm going to multiply the 8 and the minus 2, which gives me m squared plus 15m minus 16. Then I factor. This factors into m plus 16 times m minus 1, because the last have to multiply to 16, subtract to 15, and then divide, reduce in bottoms up. I started off multiplying the last number by 8. I'm going to divide the last number by 8. 16 over 8 reduces to 2. 1 over 8 doesn't reduce. I'm going to bottoms up it. So I'm going to change the first denominator to m plus 2 over 8m minus 1. Second denominator of 5m squared plus 6m minus 8, I'm going to bottoms up it again. I'm going to multiply and get m squared plus 6m minus 40. I'm going to factor. My numbers have to multiply to 40 and subtract to 6. That's going to be 10 minus 4, because 10 minus 4 is 6, and 10 times minus 4 is minus 40. I started off multiplying by 5. I'm going to end up dividing by 5. First one I divide and get m plus 2. Second one doesn't reduce, so I bottoms up and get an m minus 4. So first denominator I'm going to change to m plus 2 times 8m minus 1. Second denominator I'm going to change to m plus 2 times 5m minus 4. So getting into that, of course, I can write this as m plus 3 over m plus 2 times 8m minus 1 minus 2 over m plus 2 times 5m minus 4. So my denominators are factored. Now I need to give them what they're missing. I'm going to put a parentheses around this first m plus 3 because it'll make it easier to see what I need to do. I need to give this a 5m minus 4 because it's missing the 5m minus 4 that the second denominator has. And I need to give this an m minus 1 because that's what it's missing. So now I've made each denominator have the same three pieces. I'm going to multiply out the numerators, write the denominators in the same order. This first numerator I have to FOIL. So I'm going to do firsts of m times 5m and get 5m squared. And then outers of m times minus 4 and get minus 4m. And then inners of 3 times 5m and get plus 15m. And then lasts 3 times minus 4 and get minus 12. So that's my numerator. I'm going to write the denominator just in the order that it's in. M plus 2 times 8m minus 1 times 5m minus 4. Second fraction, I'm holding off on the minus sign. I'm multiplying the 2 by 8m and 2 times minus 1. 2 times 8m is going to give me a 16m. 2 times minus 1 is going to give me a minus 2. And because I've committed to an order to my denominator, I'm going to write that second denominator in the same order because I can shuffle these parentheses around. So now my two fractions have the same denominators. I'm going to make the two fractions into one. When I do this, I'm going to write this as a positive 11m because that's what those combine to. So when I make the two fractions into one, I'm going to have 5m squared plus 11m minus 12. I need to switch that sign. So minus 16m plus 2 over m plus 2 times 8m minus 1 times 5m minus 4. So now my two fractions have the same denominator. They're down to 1, and I'm going to combine like terms in the numerator. In this numerator, I need to do a minus 11m and minus 16m, and a minus 12 and a plus 2. The 5m squared is going to stay, but it's not going to change. The minus 11 and minus 16 give me a minus 27. The minus 12 and the positive 2 give me a minus 10. I should check to see if that numerator factors by a bottoms up factoring, but I'm pretty sure it's prime. So almost ready to check, or I am ready to check. I'm going to plug in 2 to my original problem, 2 to my answer, and I believe that this is the answer. So now I'm going to go into checking mode. So I'm going to take the original problem, change the letters to a 2, and then in my answer change the letters to a 2. So here I'm going to go 2 plus 3 over 8 times 2 squared plus 15 times 2 minus 2 minus 2 over 5 times 2 squared plus 6 times 2 minus 8. And for my answer, I'm going to go 5 times 2 squared minus 27 times 2 minus 10 over 2 plus 2 times 8 times 2 minus 1 and 5 times 2 minus 4. I'll do both of those on my calculator. Hopefully I get the same answer for each line. So top line, fraction 2 plus 3 over 2 squared plus 15 times 2 minus 2 minus fraction 2 over 5 times 2 squared plus 6 times 2 minus 8. I get 7 over 96. Do the same thing for the next fraction, my answer. So fraction 5 times 2 squared minus 27 times 2 minus 10 over 2 plus 2 times 8 times 2 minus 1 times 5 times 2 minus 4. Please be 7 over 96. Oh, negative 11 over 90. So I'm going to double check my plugging in my 2's first. So let me do this top one to make sure I actually did it right. So I'm going to go 2 plus 3 over 8 times 2 squared plus 15 times 2 minus 2 minus fraction 2 over 5 times 2 squared plus 6 times 2 minus 8. Oh, no. Obviously, I'm fatiguing. Try that again. Fraction 2 plus 3 over 8 times 2 squared plus 15 times 2 minus 2. That looks perfect. Minus fraction 2, there's delete, minus fraction 2 over 5 times 2 squared plus 6 times 2 minus 8. Really? I feel so bad about this. I get 0 twice, so it must be 0. Second one, I don't think I'm going to get 0. Fraction 5 times 2 squared minus 27 times 2 minus 10 over 2 plus 2 times 8 times 2 minus 1 times 5 times 2 minus 4. So I have a mistake, I believe, which is horrible at this point, but I'm going to try to find that mistake. So first thing, I might have factored wrong. That's factored okay, and 10. That's my factoring's okay. I checked it in my head. So this one I had to multiply by 5m minus 4. This one I had to multiply by 8m minus 1. So 5 times m is 5m squared minus 4m plus 15m minus 12. Feel good about that. 16m minus 2. Feel good about that. 5m squared. Oh, I see what I blew right here. For whatever reason, I changed this sign from plus to minus, made that wrong. So I've discovered a mistake. I think it's the only mistake. This plus 11 minus 16 is supposed to be a minus 5m. So I should have that for my answer, and then I should have factored out a 5. I should have written 5 times m squared minus m minus 2 over m plus 2 times 8m minus 1 times 5m minus 4. So this harmless little mistake of just tweaking a sign made the entire one piece of the numerator wrong, which made the entire answer wrong, and made it so my numerator could factor twice. There's a common factor of 5 that I could pull out, and after I factor out that 5, that actually factors into m plus 1 times m minus 2. So this would be the ultimate best answer for this problem. Assuming now I haven't made another mistake that I didn't catch. So now I'm going to try this and see if I can get 0, because when I plugged in 2 to the original problem I got 0. I should get 0 when I plug 2 in for this. So this checking wasn't good. I'm going to check this now. I'm going to go 5 times 2 plus 1 times 2 minus 2 over 2 plus 2, and then times 8 times 2 minus 1 times 5 times 2 minus 4, and hope like heck I get 0. So fraction 5 parentheses 2 plus 1 parentheses 2 minus 2 over 2 plus 2 times 8 times 2 minus 1 times 5 times 2 minus 4, enter, and I get 0, and that's a beautiful thing. Normally when I get 0 I like to try another number, but when you're just beat, you just live with it. So I discovered my mistake. I feel good about that. I'm going to skip the next problem and do the last two problems. Problem 40 has double bottoms up factoring again, and I just don't, I know I won't put something like 40 on there, so I'm going to skip this. You're more than welcome to give it a try and come visit me, and I'll show you how to do it. But I am going to do 42 and 44 because 42 and 44 are the kinds of problems that they're so easy that they're hard. And maybe at the beginning of the next lecture I'll do another problem like this. So to do 42, I need to make each piece a fraction. The 4 isn't a fraction, so I'm going to write it over 1. The nice thing about this problem is neither denominator has any factoring, and it's super easy to get the right, each denominator have the same fraction. I just have to multiply the 4 by x minus 3 over x minus 3, because doing that will make the denominator x minus 3. So multiplying the second fraction by x minus 3, the numerator I multiply the 4 by x and get 4x, the 4 by minus 3 and get minus 12. The denominator 1 times anything is itself. So I'm able to make the two fractions have the same denominator by not doing any factoring and only multiplying the second fraction. Now I'm going to make the two numerators into 1. And I'm going to combine like terms, which is the 2 and the minus 12. 2 minus 12 gives me minus 10. This leads me to an okay answer, but not the best answer because I can factor out a 2. And this would lead me to the best answer. I'm going to go ahead and check this by plugging in 2. So I'm going to go 2 over 2 minus 3 plus 4. And down here I'm going to go 2 times 2 minus 5 over 2 minus 3. And make sure I get the same number. If I don't, it means I made a mistake. So I'm going to go fraction 2 over 2 minus 3 plus 4. In the original problem, I get 2 when I do this. Down here, I'm going to go fraction 2 times 2 times 2 minus 5 over 2 minus 3. Please give me 2. And it did. Because I got the same result plugging into the original problem, 2 as my answer, I feel good about the work. Last problem that I'm going to do for today. Same style of problem, but a little bit harder. I'm going to write the second piece as a fraction by writing it over 1. And I'm going to multiply the second fraction by x plus 5 over x plus 5. That will make each denominator the same. The numerator I'm going to clear by multiplying x times x and x times 5. I'm going to leave the first fraction alone. But in the numerator, I'll go x times x and get an x squared, and x times 5 and get a plus 5x. Now I have the two fractions written with the same denominator. I can write their numerators next to each other and create one fraction. That's actually a correct answer, but just written in an odd order. The best answer for this, I would have the numerator written in a nice order, x squared plus 5x plus 2. The denominator still at its x plus 5. The numerator doesn't factor, so I can't do any more other than check. I'm going to plug 2 in and go 2 over 2 plus 5 plus 2. And down here I'm going to go 2 squared plus 5 times 2 plus 2 over 2 plus 5, and see how that goes. So I get 2 over 2 plus 5 plus 2. Original problem, plugging 2 in, I get 16 over 7. Now I go to my answer, 2 squared plus 5 times 2 plus 2 over 2 plus 5. I also get 16 over 7, so I feel good about that. I'm going to, if I remember when I do the next lecture, redo something like 42 and 44 just to emphasize those. I'll do a couple review problems at the beginning of the video for those of you that are as beat as I am getting this far, and then go on to the next section. Alright, that's got to be enough.